Hello everyone, welcome back to the tutorials on mechanical vibrations. Today we continue on the harmonically excited vibration of single degree of freedom systems with the focus on the systems with damping. So let's begin. So to begin, as usual, let's have a review on what a force vibration means and what is the single degree of freedom system and the damping. So as you remember, we have this general case that we have a spring, a mass, and a damping in the system. And as you remember, for the force vibration we have basically a force, and here we take it as a harmonic force, which is equal to F naught, and then depends on the harmonic term, either a cos or sine function. So for example, cos omega t is a force excitation and x is the direction of motion. So as I said, in this case we are going to focus on the system that we have a damping on the system, and therefore the equation of motion and the response of the system would be different. So the equation of motion here would be as usual with the mx double dot plus cx dot here plus kx. So last week we noticed that cx dot does not exist in the system when we have no damping, but here we have the cx dot, and eventually it's equal to the force, which is F naught cos omega t. And remember, the omega is the frequency of excitation, which is different from the natural frequency of the system. So again, this equation is a non-homogeneous differential equation. We have a homogeneous response xh, right, as we have before when force is 0, and we have a private solution or particular solution. So xp is the particular solution, which is equal to an amplitude x and cos omega t minus phi. So in fact, the frequency of the particular solution is equal to the force frequency, and x is the amplitude that we need to find for the system. The particular solution is more important than the homogeneous response, because we know because of the damping, the homogeneous response basically dissipates or disappears after a while. So let's focus on the particular solution. As we know, x, the amplitude, is a function of force and the other components of the system, such as mass, spring, and damping. For this case, it is equal to F naught divided by k minus m omega squared plus c squared omega squared to the power of half. So as you see here, we have both the effect of force amplitude, the effect of other components of the system, such as damping, stiffness, and mass. So x is basically the amplitude of the particular solution. Okay, so let's continue on the review for these systems, because there are other components that we need to know. One component that we forget to discuss in the previous slide is basically the phase of the particular solution phi, which is equal to the tan inverse of, again, the components of the system c omega divided by k minus m omega squared. So in fact, we found the two components of the private solution or the particular solution xp, which was x cos omega t minus phi. So we found x and phi. The total response of the system, again, xt, is the summation of the homogeneous part plus the particular solution, right? So this system has a damping, which means that the homogeneous part disappears after a while because of the damping, and the remaining term is the particular solution, which we also call it as the steady state response, right? Because it remains in the system. So if you may remember, the homogeneous part is the response of a system for we can find it from the free vibration of a damped system, and basically it is just the standard way we used in previous tutorials to find the response of the system, and then we can basically find the components based on the values that we have in the system. So I want to write it simply here xt is equal to x naught e minus zeta omega n t. I'm sure you are familiar with these components because we have them before. Cos omega d t minus phi naught plus, this is actually the homogeneous part, plus the private or particular solution x cos omega t minus phi. So as you see here, we have both solutions combined in one term, and therefore we can find the response accordingly, right? So if we plot the response, for example, for any arbitrary initial conditions, we will see that the response would be something like that, and after a while it becomes stable and shows the stable or the steady state condition. So this part, the initial part, is the summation, and after a while basically the homogeneous part goes away, and what's remaining is related to the particular response or steady state, right? It makes sense. So keep in mind, that's why we focus on the steady state response, and in many conditions and many problems we focus on that part of the solution. Another important consideration is when we have an initial condition and we want to apply it into our equation, we need to apply it to the total response, right? So xt. So remember, xt is applied to the, or initial condition is applied to the total response, not just the private or the homogeneous response. So keep it that mind. It is very important, and a common mistake that's made by many students, that when they want to find, for example, x naught or phi naught or x or phi, they apply it to only one part of the solution, but you have to apply it to the total response, right? Because you want to find x naught and phi naught. In the example today, we will show how to use that basically to find basically the components of the system using the initial condition. So we are all set with reviewing these types of problems, and then we can start our example. However, I want to basically show some other types of representation for response of the systems because it's very useful, and in many basically representations these types of equations are used. So basically, we are familiar with the definition of frequency ratio. So R, the frequency ratio, is a ratio between the force vibration frequency or the excitation frequency and the natural frequency of the system, where it is equal to omega n is equal to k over m. I suppose that you all know that. And there is another component, basically zeta. As you may remember, zeta is equal to c over c critical, and c critical is basically c critical is equal to 2m omega n, right? These are the components that we had before. There is another definition we use here, which is called delta static, which is the static deflection because of the amplitude of the force, and it is called as F naught over K. So keep that in mind. Why? Because in many response representations and analysis, we want to find X over delta static. And what does this ratio show? It is the ratio between the amplitude of steady state response divided by the basically the deflection under static force. So this is the deflection under static force here. And if we basically find the ratio, we already know X, we know delta static, we can simplify with respect to R and zeta, which gives us 1 over 1 minus R squared plus 2 zeta R squared. So this is another important formula or representation shown in the forced vibration of damped system, and based on the value of R and zeta, you can judge based on the response of the system. For example, if the system damps very quickly, or you have vibration, or there is a resonance in the system, and so on. And there is another important graph that I want to show you schematically here, which is basically is like a frequency type domain. So R, which is omega over omega n, and the y-axis is x over delta static, or the amplitude ratio. So we call this as amplitude ratio. So depending on the value of zeta, you can have different graphs. For example, so imagine it starts at a certain point, say for example 1, because at 0, when there is no sort of vibration, x and delta static are equal. So for large value of zeta, like huge damping, the system behaves. And one thing that we need to note is this point 1, which is equal to R, which gives us omega O is equal to omega n, right? So this is like the ratio of the frequencies are equal. So I'm going to put it in a bracket so you remember this is the case that we are discussing here. So this case relates to omega equal to omega n. So for large value of zeta, we have such behavior, right? So as you see, there is no sort of resonance in the system. That gives us a huge amplitude. And then as zeta becomes smaller, so for example, this is for zeta is like, for example, equal to 5, right? And then as zeta becomes smaller, the system behavior changes, and it depends on, for example, how big zeta is. Like this is for example 1, and then we have something like this as zeta equal to a half, and then zeta becomes smaller, and then at a very small amount of zeta, the system has a very huge amplitude, which is somehow a sort of resonance condition, for example 0.1. So remember, this is very important to know how big zeta is, and based on that your behavior would be different. And as you see, when R becomes larger, the amplitudes tend to be like to go to a sort of a small number, and also goes to a sort of constant value, like asymptotically to a constant value. This is important for the design purposes, especially for like sensing vibrations and accelerometers. You want to be beyond the resonance condition, right? Just keep that in mind. Okay, so I think we are all set with the review, and we want to have the example today and see how we can basically use the equations we have for solving one problem. So let's go to the first example, which is actually the only example we have today, because we had a long discussion on the force vibration of a damped system. And let's go over the problem and see how we can basically find the solution. So in this problem, we have a standard spring mass damper system. So I'm gonna draw it here. And we have damping in the system as well. So we have M, K, and basically C. All the values are given here. And the force applied to the system is also given. We have F equals to 200 cos 10t. So we have omega and we have F naught. So we also have the initial condition. So we want to find both the steady state response of the system and the total response of the system. So this is a very interesting and important problem, that we want to find both responses on the system. So let's have some standard calculations. And before we move forward, I should say that in many examples, the system is not standard. You have to simplify, you have to find the equivalent stiffness, equivalent damping ratio, and or damping constant, and equivalent mass of the system. So if it's more complicated, you need to simplify it first based on the methods and examples that we showed before, and then use that to find the response of the system, okay? And the rest is just simplifications and substitutions into equation. So let's find the natural frequency of the system first, omega n, which is equal to K over M. So we know K and we know M, so it gives us two like 20 radian per second, and we always use radian per second in the calculations. So the other important component that we discussed is the static deflection, which is equal to F naught over K here, which is 0.05 per meter, or like 5 centimeters. Zeta is equal to C over C critical. We also know C critical, or it's equal C over 2 omega n, which is equal to 0.1, and it has no dimension. We know that. Another component that we need to find is the damped frequency. Why? Because we are looking for the total response of the system, right? So that's why we also need to find omega d, because we need that in the future. But we know it's equal to 1 minus zeta squared times omega n. So we know zeta, we know omega n. So it's very easy to find the damped frequency, 8997. And as you see, it's nearby the undamped frequency because zeta is very small, right? And the unit is again radian per second. So we have everything now. We can simply find x. There are different methods that we can use to find x. So we have the formula x over zeta or delta static, which was equal to 1 over, you can either use the function of F naught divided by the other components, or the function based on R. I'm gonna use this one here just to know that they're basically similar, or they can be used reciprocally. So therefore we can find x as just x is equal to delta static divided by 1 minus r squared plus 2 zeta r squared. So we know zeta, we know r, and we know delta static. So the rest would be just the substitutions, which gives us 0.06608 meter. So this is actually our amplitude of the steady state response. For the steady state response, we also need to find phi, the phase, which was equal to, we have again a formula as a function of omega, c, and k. We also have a formula based on r that I didn't show before, but not a problem, we can show it here. It's equal to tan inverse of 2 zeta r divided by 1 minus r squared, right? So this is again a relationship based on r and zeta. We can also use the one based on omega, c, and f, or say m and k, right? So we have everything here. We can find the tan inverse. I don't want to spend time on the calculation, and eventually it gives us 0.1325 radian. And always remember, all these calculations gives us the angles based on radian. So we know everything. We have phi and capital X, so we can find the homogeneous or the particular response, or which is also our steady state response, as x cos omega t minus phi. So as you see, the frequency of the steady state is equal to the frequency of the force. So in fact, the system after a while vibrates with the same frequency of the excitation. So if we use the numbers we have before, it's equal to 0.06608 cos, and omega is 10 t. Yeah, you see omega is here, minus the phase, right? 2.5. That's it. Yeah, I think we can get it here. So we found the steady state response, but we still need to find the total response of the system. And as you remember, the total response is the summation of the homogeneous response and the steady state response. So xt is equal to x naught. We can also use, here I'm using x naught and phi naught. You can also use the formula based on the cos and sine combination, right? I hope you can remember that from before. So x naught e minus zeta omega n t cos omega n, or here actually let's use omega d. I just want to use omega n times 1 minus zeta squared, but why don't we use the omega d, because we already calculated that. So omega d t minus phi naught plus the private solution plus x cos omega t minus phi, right? So we found this part. We need to find x naught and phi naught, and to do that we need to apply initial condition to the total response. Keep that in mind. So let's just do this. So for initial conditions, we have x at 0, which is x naught, and we have x dot at 0, which is equal to x dot naught. We know those values. It was defined, they were defined in the problem. So what is x naught? Just simply plug in 0 in the above equation. It's equal to x naught cos phi naught plus x cos phi, right? So we don't even need a bracket here, so that's it. And to find x dot naught, just take the derivative and then plug in 0 for t. So this gives us minus zeta omega n x naught cos phi naught plus omega d x naught sine phi naught. This is from the first part and the derivation, and then we have the derivative of the steady state, which is omega x sine phi, right? I'm sure you can find that because it's just a derivation, and we plug in the numbers. Okay, so we can further simplify these two equations. So if we look at the for example, if I want to use a different color, so in here, like in this equation, we can find these terms, and also we can simplify for this, and I tell you why. Let's simplify for this term, right? So we have x dot naught, right, sine phi naught is equal to 1 over omega d times x dot naught, which is here, and this term goes to the left hand side, plus zeta omega n x naught cos phi naught minus omega x sine phi, right? This one goes to the left hand side. So we found the expression for x naught sine phi naught, and from here we want to find the expression for x naught cos phi naught, which is, like, it is very simple to find it here. It's equal to x naught minus, we just take this term to the left hand side, x cos phi. So why we did that? Because we want to make x naught sine this equation phi naught and x naught cos phi naught. We can then square them and then sum them up to get rid of the sine phi naught and cos phi naught to find x naught, right? So let's plug in the values we have here. So basically, if we look at it here, we have x dot naught from the initial conditions. We know basically these values. This part can come from here, right? And then we have x naught and x cos phi. So we can simply find these two equations. Again, how we can find these two equations? For this part, it's pretty easy, right? Because we know x naught, and then we have x cos phi from before, right? Because we found x and phi. For the top equation in here, after we find x naught cos phi naught, we just go and use it in here. We know this one and that one, and then we can find the top equation as well. So let's plug in and see what we get afterward. So if we plug in the values that we have, we can find x naught cos phi naught equal to 0.03448, and then we can find x naught sine phi naught equal to minus 0.000922. So then it's pretty easy, just square this equation and then square that equation and then sum them up. So what we have here, we can simply find, so if we square that one and then basically we have x squared cos squared phi plus x squared cos squared phi naught equals to x. I'm sure you know this, and sorry, I just have to use a sign here. So this is a sine squared phi naught. This is just doing math and trigonometry, right, which is equal to 1, right? So basically x is equal to the square root of this term, right? And where is this coming from? We can use the two numbers here. So it's 0.034498 squared plus minus 0.000922 squared, which gives us the value of x naught, which is 0.0345, and it is meter, right? So we found x naught, the amplitude from the homogeneous part. For phi naught, it's even easier, because if we look at these two equations and then we divide them, it's equal to the tan inverse of x naught sine phi naught divided by x naught cos phi naught, right? We just need to divide these two values, and then we find phi naught as minus 0.0267, and this is radian, right? So basically, and not to forget, I'm gonna use meter for this one. So we found the amplitude and the phase of the homogeneous part, and then we can plug it into our total response, the formula that we have before. So basically the formula we had for the xt was the private solution, and the homogeneous part is hh plus xp, which gives us, so xt, the total response is what we found before, x naught, the capital X naught, 345 e minus zeta omega n t, which is, let me just use the number. So we have 2t cos the damped frequency 19.899.7t, or maybe other terms that I missed, plus phi naught, the phase of the homogeneous part, 267, we just found it, plus the private or the steady state response, 6608, which is x, capital X, cos the force frequency 10t minus the phase phi 313255. So we found the total response of the system. So as you noticed, it's a bit exhaustive and you have to do a lot of calculations, but it is pretty straightforward. Just plug in the initial conditions and find x naught and phi naught, because we already have x and phi, right? So in this example, we discussed the case that we have a standard harmonic force applied to a damped system. In the future, we focus on basically the case that we have base excitation or eccentric mass. You'll see that it is similar to the case that we have a standard force, but with some differences in terms of the force, amplitude, or basically the final response of the system. So I hope you enjoyed the video, and please stay tuned for the next videos. Thank you.